Greetings, everyone. My name is Umair bin Wahid, and in this presentation, I'll walk you through the idea of using double difference seismic tomography using physics-informed neural networks. I'd like to acknowledge my co-authors here, Chris Huber and George Kanadakis from Brown University. All right, so seismic tomography has been used, a preeminent tool to image the subsurface structures at various scales, essentially from global to regional scale in earthquake seismology to local scales in exploration seismology. Typically, seismic tomography is performed using a array-based method or adjoint-based formulation. However, these conventional tomography methods suffer from several limitations, including the need for a smoothing regularizer to overcome the issue of ill-posedness of the inverse problem, sensitivity to the initial model. So if you start with an initial model is far away or is something that is very different from the actual model, then it can lead to some unphysical inversion models as well. Also, we have this problem of algorithmic complexity for irregular topography. So if you want to model irregular topography, you need to either do some sort of mathematical flattening of that topography layer or use some more complicated methods like spectral element methods, for example. And there's also another issue of the lack of portability between different hardwares. So if you have your codes for a CPU machine and then you want to run them on GPUs, you will have to rewrite those codes. So PINNTomo, as we presented last year at the AGU meeting, overcomes these let's say, limitations of conventional tomography methods. In case you're not familiar with PINs or physics-informed neural networks, let me quickly go over this so that all of us are on the same page. So how can we make a neural network solve a partial differential equation? That's essentially the idea here. So neural networks, as we know, are function approximators. So you want to approximate this function u, which represents our variable of interest, and it depends on the spatial and temporal coordinates, x and t, for example. And the way we would do it is we would train this neural network over some collection of grid points, which covers our computational domain between x and t. And in that domain, we're trying to solve the partial differential equation. So how we would do it is we would calculate the derivative of u with respect to the inputs. So it could be the first order or the higher order derivatives. And we could do this very easily through automatic differentiation, which is, let's say, a generalized technique of the backpropagation algorithm, where we use chain rule to sequentially go back to the different weights that we want to update. In this case, we go all the way back to the inputs. And once we have these derivatives, we can plug them into the original partial differential equation or the residual form of it, and that forms one part of your loss function, and combine that with the boundary conditions that you have, or the initial condition, or any existing data, and that forms the loss function that will drive the optimization process, and will eventually lead to solving this partial differential equation if we could show that it could converge to some minima of this loss function. So that's the idea behind solving a partial differential equation using physics-informed neural networks. So now what can we do now to solve an inverse problem? So essentially, let's take this example of a PINNTomo, or physics-informed neural network-based tomography method. In this case, what we have is the first one is the travel time network, or the network that, given some source and receiver coordinates, gives us the travel time value from that source to the receiver. Okay, and we have this velocity network, which, given some coordinates in your computational domain, will spit out the velocity at those coordinates. Of course, we don't need source locations for the velocity network because it does not depend on it, right? And in our loss function this time, we have two terms. So one is the data mismatch term, that is, at some observation points, we ask the network to predict travel time values that match those we have observed. So it only happens, of course, at those observation points where we have some values for the travel time picks. And the other loss function, and the other component of the loss function is the residual of the iconal equation that combines the velocity predicted by the second network and the travel time predicted by the first network in that iconal equation. So this is essentially what we do, that we are trying to predict travel times and velocity values that not only match the data that we have observed, but in the process also satisfy the underlying partial differential equation or the physics of the problem, which is governed by the Eikonal equation. Now, one good thing about this is that we have this Eikonal residual term that acts as a physics-informed regularizer, which I believe is a better way to address the ill-posedness issue, that is using physics rather than using some form of smoothing regularizers, which end up limiting the resolution of your model. Now, going to how we can incorporate, or why do we need to incorporate this double difference idea into the PIN-tomography workflow, is that we notice that the PIN-tomo algorithm takes plenty of training epochs to converge to the solution, and therefore we're looking for ways in order to accelerate this. And one idea is to use this differential travel times. And in addition to the absolute travel times, we also use differential travel times from two sources. So imagine you have you take a pair of sources, and then you have a single receiver, and then you're not only trying to fit the absolute travel times from these two sources to this receiver, but also their differential travel times. And it's been shown in many papers in earthquake seismology that these differential travel times give us a much better, let's say, structure close to these sources, and therefore it helps converge to a better solution. And in this case, we observe that it also speeds up our convergence by helping the algorithm learn or train faster. In this case, what we have is the travel time network, of course, has two pairs of sources, right? Two sources, sorry, and a receiver location. And then the velocity network only depends on coordinates from your domain. So essentially, there are two terms for absolute data mismatch, one term for differential data mismatch, and one term for the Eikonal residual. So let's take a quick look at how this works compared to PINTomo for a cross-hole tomography example. So we have our sources here on the left, 11 sources at a spacing of 100 meters. On the right are 51 receivers at a spacing of 20 meters. These are the results. So on the left is the true velocity model. In the middle is the one obtained using PINTomo without double difference, and on the right is the one with double differences. We can clearly see the quality of the inverted solution is much better than what we get with PINTomo. And of course, we do this for a certain number of epochs to ensure that the comparison is fair in both cases. And if we could run this for more epochs, it takes more time, but for PINTomo, it could also give a value that is something, or an inverted model that is something close to this. So that's what we expect from tomography, travel time-based tomography algorithm, to give us a smooth update of the velocity model, which can then be used for full waveform inversion. Now, one thing to note here is the starting model for both these, let's say, algorithms, PINTomo or PINNTomoDD, were chosen randomly. And this is one of the advantage here, is that the method is quite robust to bad initial velocity model choices. And therefore, we choose something really random and show that we could converge very close to the actual solution. And here are the loss curves here. So in blue is the loss curve for PINTomo, which shows that it will take a while before it could converge to a loss value that PINTomoDD could converge to much faster. With that, I'd like to thank you all for listening. If you have any questions, please feel free to email me at umair.waheed@kvpm.edu.sa. And if you have anything to discuss, you're most welcome to do that. I'm also open to collaboration opportunities. So please feel free to write me an email if you are interested in this. I'd also like to acknowledge my research group, Smart Earth Exploration and Monitoring, and King Fahd University of Petroleum and Minerals for their support. Thank you very much for listening to this talk.